In addition to SVMs and random forests, we also tried developing our own homegrown convolutional neural network for image classification. Images were resized to 224 by 224 in order to maintain a decent amount of image detail. Augmentation was applied to the training data. This consisted of flipping images, rotating them within a certain range, and shearing them as well. The augmented training data helps the CNN be exposed to a more diverse set of images, which can help prevent overfitting and consequently help with class generalization. An Adagrad optimizer was used because it has an adaptive learning rate, and that's beneficial for really long training periods for CNNs like ours. And we used a categorical cross entropy loss as the loss type for the optimizer. So here's the CNN architecture. It looks a little different than last time, mainly because I found an error in the training code that I had made. I was accidentally augmenting the test data as well, and that's really a no-no because that's not a decent and fair evaluation of the model's performance on future data. However, fortunately, this model was now the best performing model, and it's a bit smaller than the last one, so it's a bit less unwieldy, trains a bit quicker. The neural network is still quite complex. You see each layer there has uh, over 4,000 nodes each, and there's a fairly weak dropout rate, so there are a lot of calculations occurring there. Softmax is still used as the output, so that we have a percent likelihood for what class we are determining the image belongs to. And here is just an example of some of the output layers from the CNN. We can see here that over time it has learned to apply certain filters, which are sets of weights that prove beneficial for classifying particular portions of images or an image as a whole and identifying that as the target class. So you can see here as we apply filters and shrink the images, you do lose a bit of that resolution. We have much clearer pictures on the left there in the first set of filters, and as we get towards the end, it gets a lot more rough. But that is the output that will go to the neural network and is therefore classified as whatever car the model thinks it is. And last, our performance was a little bit different than last time. Like I said, I had found that error and I wasn't correctly testing on the appropriate image set. But after that correction, we found that the CNN that we developed levels out at about 30% validation accuracy. It took about 200 epochs to really settle, as you can see there. It had okay top 5 validation accuracy. What this means is that about half the time the correct class identification will be within the top 5. So not stellar performance and a little worse than last time, but again, uh, this is a more fair assessment of the model's performance on hypothetical future data.